So in the future, you can go to, so the spreadsheet is the source of everything, right? And then if you go to this online web page for the course, so let me say course web page. Then you will see a table for this particular course, and I will be posting online information for every semester. As you can see, for today I haven't put anything yet, but from last year you can see that I use the same PowerPoint. So since 111-1, I think I didn't change my slide too much. So you can actually check many of the old files. I will be using those. And also, if you click on live lecture or some of the clicks like video, those were the online lecture videos. So if you feel like this week I'm not doing pretty well, maybe a year ago I could be doing a better job, so you can check all videos. But anyway, so this is somewhere you can find my course information. And for Taiwanese, if you you want to double check what I have talked about, I do have some of the Chinese version videos and information. So it's really up to you. They are all open to anyone, so you can download at any time. Back to what I want to work on today. So let me see how I make it full screen. Maybe I open in a different software. Okay, great. Now, there's a, so who has heard of safety factor? Anyone? Yeah. So, but what is the safety factor?
So it's the ratio between
Come in.
what?
Yeah, go ahead. Ratio of what?
Between allowed stress and maximum stress. Yeah.
Exactly. So when did you learn about this?
Mechanical materials and
Yes. So in the many of the solid mechanics courses, we talk about safety factor already. But have you heard of von Mises stress? There's like an equivalent stress. Or have you heard of fatigue model? Okay. Yeah. So in solid mechanics, we don't talk too much about those because they are something we need to learn after we master solid mechanics. So for solid mechanics, we figure out the stress distribution inside any kind of part, some kind of part in a particular shape, and then figure out which part is carrying more loads. That's it. That's the end. We never do anything further. We never say, okay, in the design viewpoint, we should be maybe make some kind of dimensional change so the part becomes safer. We never do that. This is what you need to learn in this course. So it's a follow-up from the previous course. Okay? So, in solid mechanics, probably you solve a plate problem. You have some supports, you have some force. You will know, okay, there's some stress distribution here. That's it. No one have taught you what to do afterward. So take this table as an example. If I apply too large of a force, then maybe at somewhere at the connection part, underneath the table or somewhere that is weak, the weakest, that would be carrying the most load. So somewhere inside this table will start to break. Okay, that's the worst case position. In this course, we need to figure out where is the worst case position. Which position breaks first? And there are two kinds of failure. If I apply a strong force like this, maybe some bolt right there cannot carry the load anymore. One day the bolt will crack. So this is so-called the static load. The force doesn't change with time if I just apply a force like this. But there's a different kind of load, like this, fluctuating. The force changes with time. So if I have this kind of dynamic force or fluctuating force applied to anything, there is a different kind of failure, so-called fatigue. So for everything, there are two different ways of failure. One is just breakage. The other one is fatigue. So in the first part of the lecture, we talk about static load and how a part could be failing. Second part, we talk about dynamic loads. We will give you some models about design for fatigue. Okay. Then we will move on to some of the popular mechanical parts in different kinds of mechanical parts. For example, spring, screw and bolt, or bearing, or even a cylinder, a cylindrical rod, or gears, pulley. There are so many different kinds of mechanical parts. They all look different, and the way they carry loads are different, so their failure modes are different. So the difficulty of learning this course sometimes is because in the second half of the textbook, there are so many different kinds of parts. Each kind of mechanical part is like an individual study. You can even take a whole course for that particular part. For example, gear design. Like in our department, there's a professor Shi Yipei. She is an expert in gears. She can give a lecture about gears for the whole semester. But in this course, we cannot do that. For every mechanical part, we probably only spend 1 week. So it's impossible for me to cover the whole book. Do you have my book? No book, right? It's okay. Your cover. It's okay. So if you buy the book, or if you have a book, or if you borrow a book from someone, we are using this book, Shigley's Mechanical Engineering Design book. It's a thick book. So we follow the chapter inside the book. If I show you some of the chapters in the book, I do have some of the copies, like the PowerPoints. Okay, take like chapter 6, I think it's about mechanics. Like this is about fatigue, right? Chapter 5 is about static load, failure due to static load. Chapter 6, different kind of failure due to fatigue. 疲劳 is fatigue. Okay, like, and then what's about chapter 8? Chapter 8, starting from some kind of mechanical part, screws. Chapter 9, welding parts. They are completely different kinds of mechanical parts. So when I was a student, when I took the course, every week I was like learning something new. And I realized, how come did I fall asleep last time? How come today's lecture is so different from last week? This is how this course was supposed to be, because we need to learn mechanics for different kinds of parts and failure modes for different kinds of parts. And sometimes they are not even the same. They are not too much related. So you will be learning different parts and very different from others. So to teach this course is very challenging because you may get lost easily. But I always think this book is a really good reference book because later on in the future, as a mechanical engineer, one day you probably will be asked to design a mechanical part. Or some kind of system that consists of multiple parts. If it's your responsibility to decide the dimensions of all parts, or if you have some commercial available products such as bearings, you need to decide which size you choose. The specification of all available parts. So you are the person who make the decision. If you overly design, which means you make something too strong, yes, the whole thing is very strong, it doesn't fail, but that means you lose money. Your company lose money. For example, if you make if you are a vehicle designer, you are making your car is so strong, then your car becomes too heavy, then the energy efficiency is very low. It's it burns the gasoline too fast, right? So if you want to make energy efficiency higher, you may want to lower the weight. So for some of the parts, you may want to make it smaller, like a cylinder. You can change the diameter of the cylinder. You can make it thinner, or thickness of some kind of plate of the wall, or some kind of shell. You can make it thinner. But whenever you do that, by common sense, it's becoming weaker. So there's always a trade-off. Strong but heavy, lightweight but weak. How do you find the balance? Okay, so usually it requires some kind of statistics. 统计 statistics. So we need to study what's the failure rate. If I can make a part, out of 1,000, only one part will fail. Then the failure rate will be 1 over 1,000. Maybe for the company, that's a really good success rate because many 9s over 1,000. That's a success rate, right? 999 over 1,000. So the success rate, 99.9%. Maybe it's good. Or for semiconductor, no, it's not good. You need more 9s, 99.999, you need a lot of 9s. Then you can only allow one failure out of maybe 1 million parts. So for different company, different application, the required success rate is different. Let's talk about the safety design for the elevator. Do you want to allow 1% of failure rate? That means you go into the elevator for 100 times, one time you'll be dead. So for human safety, you need super high reliability. You only can tolerate very, very small failure rate. So in that particular example, elevator, you need super high safety. For the desk right here, if I'm a chubby professor, one day I sit right here, I put my whole weight over here, and then some part breaks, but nothing happened. I just damage a desk. It doesn't kill me. I just need to pay back to the school, or I just say nothing. So nothing happened. So maybe the design for the desk doesn't need to be that safe compared to elevator. Okay, so as an engineer, you need to know how much safety you apply. So over here in my slide, you realize there's a concept, so-called the safety factor, right? And Peter just said it right. It's a ratio of how strong your part is over how much force you apply to it. So usually you want your strength to be greater than the force applied to your body, right? So if this is doubled, that means you are like 2 times stronger than the force. So take my arm as an example. If there's someone pulling my arm, and if I'm not strong enough, that pulling force will break my arm. But if I'm double stronger than the pulling force, then I'm okay. I'm 2 times safer. So this ratio usually has to be greater than 1. If it equals to 1, it's like, okay, the pulling force is about to break my arm because the pulling force equals to the strength of my arm. So if the force is slightly stronger, then my arm was broken. Right? So usually we want this number to be greater than 1 or even higher. For elevator, probably safety factor 10. For desk, probably safety factor only 2. So from here you can see in different applications, they use different safety factor. So how do we know how much safety factor we need to apply? Actually, we don't know. It really depends on the manufacturer. They have done this business for many years, and they have the experience, and they have their business strategy. Like when I was a young kid, we have the Datong rice cooker in every Taiwanese family. Our rice cooker from Datong was so strong, usually you can use it for 30 years without breaking. Because at the time, they didn't apply reliability engineering. They tend to make something too strong. So actually, because our rice cookers was too strong, it doesn't break. Of course, we love our Datong rice cooker, but we don't buy a second one. So this company doesn't make bigger money. So that if Datong has Steve Jobs, then you have rice cooker 1, rice cooker 2, rice cooker 16, right? Like our iPhone. So now I have an iPhone 15 and the 16 is out. Should I buy a new one? Right? So it's a safety factor also is a strategy. And nowadays our cell phone will be dead in 2 years, 3 years, mostly because of the battery or the Wi-Fi connection become weaker. How come? How come the battery can only last for 3 years and the Wi-Fi connection gets weaker and weaker? Because they are doing super good job in reliability engineering. They are making sure some of the electronic parts will get weaker and weaker day by day until the warranty is dead. Something will be broken. So you will decide. Should I pay more money to buy a new component or just buy a new one? So that's the strategy of warranty. So due to the advance of reliability engineering, nowadays we keep on changing new commercial products because they are doing such a good job. Okay? So, as engineers, in the future, when you go to a company, your job probably is to make the right decision so it's safe enough, not too safe, not too weak. If it's too safe, company lose money. If too weak, you have customers complain or someone's dead. Right? So you need to do it exactly the right way. So in today's course, we need to figure out, in this course, we need to figure out how to do it. Now, get back to mechanics. So for every individual tiny bit inside a material, you can make a cartoon like a cube. You can treat a small dot as a cube, and then you can figure out several different faces from different directions of the cube, and you can set up some kind of coordinate system, Cartesian coordinate system. In this way, x, y, and z. And then you can figure out, okay, on different planes, you may have stresses along certain direction or lying on the surface of certain face. Then we label them by the indexes. So in general, we have sigma I and j. First one represents its direction. Second one, first one represents location. Second one represents direction. Take this one YY as an example. So sigma YY is located on this plane facing Y direction, something like this. Okay, so you need to now make sure you remember this. This is a very basic. Okay, so the stresses that is facing outward toward a plane, if it's perpendicular, we call them normal stresses. If it's lying on the surface, we call them shearing stresses. Okay? So, and we actually need to figure out safety factor based on all the stresses. So there could be one of the stress along certain direction that is super large. Then because due to the safety factor you decided, your material has to be super strong, n times larger, stronger than the stress. Okay, so that's why you need to figure out all the stresses everywhere along every direction. Is any of the stress that is too large, then the material may crack along that direction because maybe along certain direction the stress is too large. If you are not doing a good job on analyzing the stresses, you miscalculate something, then you may have failure. So, some reminder to elastic mechanics. So basically, the amount of stress applied to the material generates some kind of strain, and the stress and strain are still having some kind of linear relationship. We call this region the elastic mechanics region. For mechanical parts, most of the time, we only deal with elastic mechanics. Can someone tell me why? Like for this particular design, when we design this, we should only study within elastic mechanics region. Why not focusing on the nonlinear force part? Anyone? Okay, so the difference between the linear region and the nonlinear region is right here. It's called the yielding position, right? Yielding point. So after yielding, the material cannot recover back to its own shape. So if we design for a certain region right here, that means we are allowing some part to be elongate, pass through the yielding point, and being expanded to certain shape, it doesn't recover back. Do you want your bicycle, riding your bicycle, and one day, because you ride through a hole on the street, so you can bump into the street, and then very strong force applied to your bicycle, and because the force was too large, so the strain, basically deformation, was larger than yielding point. So it becomes nonlinear deformation, and it doesn't recover back to its own shape. Do you want your bicycle to be changing its shape after bumping into a hole? No, right? So as a designer, we need to make sure the bicycle is strong enough and it can carry certain amount of load. When we are riding the bicycle and all kinds of load applied to the bicycle is within elastic region, supposedly after you release the force, it recovers back to its original shape. So that's what engineers need to do. So that's why in this course usually we don't even need to touch nonlinear region. In advanced mechanics course, of course we learn something about nonlinear mechanics. We learn about what will happen if we apply a force that is too strong. So we get to know more about the materials. But in this course, we don't want this to happen. We want to keep our design safe within elastic region. So that's the usual case. Okay, so let's review some of the equations. By definition, stress equals to the force over the effective area. Okay, if it's a normal stress, so basically if I apply some kind of compression, like how much force I will apply, divided by the circular area, the effective area that carries my force, then I know what's the stress accumulated inside this cylinder, right? So if I do shearing, for example, I am shearing like this, okay, the pulling force and the effective area, then I know what will be the shearing stress. Okay, strain, by definition, basically is the delta over L, basically the amount of the deformation over its original length. Okay, so linear relationship between the stress and strain, we use a factor called Young's modulus to define this linear relationship. So by all three equations, you put everything together, you end up with delta equals to PL over EA. So you can compute how much deformation you will have based on how much force is applied, what's the original length, what's the Young's modulus, and what's the area. Then you can compute how much deformation you have. Okay, from this figure, two important points you need to know. Yielding point, this is the yielding point. Ultimate tensile strength, basically how the extreme tensile stress this material can carry. This material cannot carry even larger force. It basically just non-linearly expand and then about to crack. Okay, so that's elasticity. And now we're moving. You may think, okay, I talk too much for each slide, but you can see the knowledge advanced quite quickly. Now we are already reviewing bending. Okay, bending is a very common force that you will see in all kinds of mechanical parts. Take this rectangular box as an example. If you draw the coordinate system in this way, this is x, this is y, and if you bend in this way by this bending moment, right? Then what's inside the material comes out like this. Due to this bending over here at the upper part, upper half, everywhere inside this upper half is being pulled toward from both sides, right? It's being pulled, being tension, right? Tension being applied everywhere for the upper part. And for the bottom part, because you are bending this way, the bottom part is being compressed. So if the upper part tension, the lower half is compressed, then there will be somewhere at the middle, it's right somewhere you have no force. So there's a neutral plane where you have no force. So over there, how do you define there's no force? Basically, no deformation. If no force, then no deformation. Okay, so in the 3D drawing, you can also visualize how it looks like. Okay, these are stresses are coming out like this way, so it's being pulled, and this is the bottom half is being compressed. Okay, so we need to know how to do calculations for these. So we use balance of moment. How do we do that? Let's use the left lower corner drawing to start. So over here, if you cut that geometry in half, so all these stresses basically are the stresses applied from its neighboring the other half of the material. So it's like because of bending at the upper part, the material on the right hand side is pulling the left part of this material. And for the bottom side, the material on the right is pushing toward the material right here. So we assume this distribution is a linear distribution because we are dealing, everything is linear. So we just assume here we should have zero stress, and at the edge, supposedly we should have the strongest stress. So it's a model where we assume the stress is K times the investigation point Y right here. So when Y equals to 0, you are right at the neutral point. When Y equals to the half of the height, you have the largest stress. So that you can draw a linear stress distribution like this, where the neutral has 0 stress, and the upper half is having the largest tension, where you have positive. If you call this positive Y, then this is positive sigma. And if you go down from here, you have negative Y. So over here you have negative sigma. So negative sigma represents compression. Okay? So from here, can we do some analysis so that this material itself is having a balance of moment? So over here on the left-hand side, you have the external moment that's being applied. And on the right-hand side, you have the stress distribution from its neighboring material. So over here, because we know we have this linear stress distribution, so we just need to cut those into small pieces, compute the force apply to each small portion and how it contributes to the moment. So for every small portion, we compute the moment due to those stress, sum them up. Supposedly the total stress and the total moment integrated together should be balanced out by the external moment you generate on the left. Okay? So that's why we use calculus. So we cut the area into a small, tiny bit, like a very thin area with a tiny height, dy. And so the area equals to dy times b, the width. So we call this area dA. So let's take a look at the the area dA and see what would be the force on top of dA. So the force on top of dA basically would be stress times area, right? Stress times area equals to force. So right here, right at this position, the stress is sigma y times the area. So this portion would be the force applied onto the red area. And if you use the force times the radius, then you have what? Moment, right? So this will be the radius. So the radius is the y, force is sigma dA. So this represents the moment contributed by this on top of this small area. And then we use integral from negative c to positive c. That means we sum everything up together, right? So this means summation from negative c to positive c. So this is why the total moment equals to the right-hand side. So the rest will be just math. So over here, we already know sigma equals to ky. Just plug it in. Then you have, you just reorganize everything. Then you have ky squared dA. Okay, so we figure out k is just a constant. It has nothing to do with the position of c. So k can be taken out. And you can see something computes k. K equals to m over this guy right here. So that would be defined as the area moment of inertia. Okay? If that's area moment of inertia, if this whole thing is I, if that is I, then you plug back sigma equals to m over I times y. Sigma equals to m over I times y. Right? So if this is I, then you can do this. So the next thing would be how do you compute I? So I is so-called the area moment of inertia about the rotational axis. Okay, so for square, the cross section, right, like this. Now, if you have your coordinate system, so usually from the textbook, you can check the back side, the last several pages of the textbook. You sometimes see this, or you can Google for it. Sometimes it tells you, oh, Ix and Iy, and you draw a picture like this. Okay, in this particular case, this is B, same as our B right here. This is H, same as our H right here. Same math symbol, but the coordinate is different. Over here, horizontal is X, vertical is Y, but in our figure, horizontal is actually Z, right? X, Y, and Z. And the vertical one is Y. Okay, so when we are doing the bending in this particular drawing, we are actually bending about z-axis. So on the left hand side is bending this way, on the right hand side is bending this way. But it's all about the z-axis. Okay? So actually, when we view this from the side, this is our z-axis. But in textbook, it's the horizontal x figure. So in the textbook, it tells you along this coordinate, the horizontal one is called ix. So the x here is telling you about which axis is that you are bending about. Okay, so over here we are bending about the z-axis. So if you map it with the textbook, we should be checking on the moment of inertia about the horizontal axis, which will be ix. So we should be using this equation. Okay, so over here, there was a proof. Okay, if I compute this whole thing by the equation right here, just truly implementing everything, it ends up with this equation, BH cubed over 12. And from the textbook, same, BH cubed over 12. So in the future, you can use the textbook. And if one day, this cross-section is not a box anymore, it's a circle, then you don't need to do the integral anymore. You just check the textbook. Okay, but you just need to know which axis are you rotating about, which axis are you bending about. In this particular case, you are bending about the z-axis. So in this figure, the horizontal axis. Then you should choose the area moment of inertia about the horizontal axis. But if one day, for the same geometry, you're bending this way, then you are bending about the y-axis, right? So if you're bending about the y-axis, then you should use the vertical one right here. So that's usually, you can make a mistake, okay? So that will be some reminder for your solid mechanics. I believe you have learned this. Maybe, okay, this is boring, I know this, I'm good at this. Or maybe you forget. That's fine. I already spent some time talking about this. So I think if you forget, you can later on check those equations again. Now, but we never talk about bending about the along the actual direction. So when we have something that is long, you call this bending, but you don't call this bending, right? So you usually call this motion twisting. So for solid mechanics, there's a separation. When you have a long object and you have this kind of motion, then we call it a twisting. So this is it's like a rotational moment, but it's now twisting about the long axis. So in this way, it's going to be shearing force, not bending force anymore. So we need to take a look at this figure right here. So now it's it's like a rotational kind of force applied about the center axis, not bending anymore. Now, originally, there is a dashed line right here. After the twisting, if you have a twisting moment, basically, usually it comes with a pair. This one going, if you call this clockwise, then this one goes counterclockwise. Then you are doing some kind of twisting like this. Right? So after this kind of twisting, if we exaggerate how much angle that was twisted, this dashed line could be twisted up to here, and there is a twisting angle. Okay, so that we call that angle gamma. But this is a very exaggerated drawing. Usually, this angle is super small, like 1 or 2 degrees. But after exaggeration, you can see over here, it generates some kind of arc from this point to this point. And there's an arc angle, theta, right there. Okay, and we want to investigate positions at different radius. And we notice that right at the edge of this cylinder, you have the largest deformation because of the twisting. So if there is the largest deformation, supposedly you should have the largest stress. But right at the middle, it's a point. Even after twisting, there's no deformation. It's still a point, same point. So right at the middle, there's no stress. That's why it's reasonable to assume the stress accumulated inside the cylinder is going to follow this kind of linear equation again. So the stress now lies on the cross-section cross-section plane, lies on the cross-section plane, and right in the middle, the shearing stress should be 0, and right at the border, right at the edge, you have the largest shearing stress. And the more you walk toward the edge, the greater your stress will be. So we assume it's going to be k times of your radius. We just don't know what k is at this moment. But we can, it's reasonable to define this shearing stress as a linear model based on the reason I just mentioned. Okay, so now we just need to focus on certain level of this circular cross-section and then figure out what would be the twisting moment generated due to the twisting force. And then sum them up. After you sum up all the twisting moment accumulated at different radius, the total torque should equals to the external torque you apply. That's basically is the same idea as the previous slide. So let me finish this page, then we can take a rest. So how do we do this? This time we'll focus on a ring right at the radius r. So the ring has a tiny thickness dr. So the area would be dA. So how do you compute dA? So basically the parameter times the thickness. So it's going to be 2 pi r times dr, right? But we don't even need it right here, because I didn't prove J anymore in this slide yet. So if we know this area, and we know the force is gonna be tangent to the radius all the time, so it's like tangent everywhere around on this ring, and they are having the same force. So how much force you have? So basically, stress times area. That will be the force lie on the ring. Total force lie on the ring. So stress times area. So stress is tau, area is dA. Stress times area. This is the force lie on the ring. All the tangent forces lie on the ring. Times the radius, what's that? Basically the moment twisting around on this ring. So only the moment apply on this pink area. So this will be the tangent forces times radius. So this will be the twisting moment only on the ring. But if I do integral from radius 0 to radius capitalized R, then I sum up all the twisting moment from R0 to big R. The total moment, sum them up, should equals to the balancing torque that was applied in advance. That's why we have this equation. It's basically the same idea, but we're doing this whole thing in this polar coordinate. Now, we know tau equals to k. I just apply back. So we have a k r squared term right there. And because the same trick again, k is a constant. It has nothing to do with the radius or the position. So k can be taken out. So k equals to t over this term right here. And this guy is again the area moment of inertia. But this is now represented as a j, not I anymore. Because previously, if you have bending about x-axis or y-axis, it's like a bending this way or this way. But now we are bending about z direction. And when we do this kind of bending, we don't call it bending anymore, we call it twisting. So basically, if you are doing this, then you are calculating j. Then how do you compute j? If you check the textbook, usually it tells you j equals to ix plus iy. Okay? So sometimes it doesn't tell you. Okay? So if you sum them up, that's your j. Okay? Or you can try to solve the integral by yourself. So anyway, similar to normal stress, for the shearing stress, you have similar equations like these. This is the shearing stress. Basically, this is a shearing strain. So this is how much you deform and in the angle. And they are having a linear relationship with a constant coefficient. So that's called G, is the shearing modulus. Okay, and also right here we have a geometrical parameter, a geometrical equation. Why do we have that? Because we have this common arc length. You use capital R times theta, that equals to this arc length. This also equals to the length right here times the angle right here. So also equals to L times gamma. With that geometrical information, you plug in, you combine both together. So at the end, you can compute how much angle is gonna twist, how much theta you have based on the above equation. So at the end, theta can be defined by how much torque you apply, how long your geometry is, over how strong the material is in the shearings fashion. So shearing module, and J, the cross-section area. So J is the area moment of inertia for the, this is called the polar area moment of inertia. Okay, so I think I want to take a break right now, because I think you guys are getting bored. So you are about to reach the fatigue zone. So let's take a break, and we will come back 5 minutes, okay? So let's do 5-minute break. If you have any questions, you can come here. Let's get back to our lecture. Now, we already reviewed bending stress and shearing stress and the related equations. So for bending and twisting of a shaft, why do we focus on a shaft? Because in many machines, whenever you need to make any movement or transmit some kind of power, usually you have a shaft. Think about it. If you have a machine, usually there's a shaft or some kind of cylindrical rod, right? Because you usually have a driving force of a motor, and then usually the force is being transmitted to a shaft, maybe by a pulley or by a chain, by some kind of connecting geometry or gears, and then by the rotation of the rod, you have some other connecting parts on top of the cylinder. Those forces are being transmitted to some other parts by gears, by pulley, and some those geometries. So usually this shaft will be carrying a lot of load. That's why it's very important. And many of the parts that we learn in the future are installed on the shaft. Okay? So in this course, later on, if we do a project, I will add, maybe your project will be very related to a shaft design in a machine, in a robot, or in something. Okay? So let's talk about the equations that we covered earlier. This is the normal stress, this is the twisting stress, right? The bending stress and the twisting stress. We already know the equation. And like I said earlier, we need to check on the textbook. For a shaft, it's having a circular cross-section. You can compute the area moment of inertia, bending about the horizontal axis or bending about the vertical axis, or twisting about the center axis. So J, IZ right here is basically J. So J equals to Ix plus Iy. So over here you can see it's double of your Ix or Iy. And because this is symmetric, Ix equals to Iy. Okay, if you apply this to the equation that we derived earlier, right here, we now change everything from radius to diameter. So here is the radius, is half of the diameter. And for the I, here we can, this is because of bending. So bending, we can choose this one or this one, the same. So pi over 4 times radius for the 4 times, right? So we just plug in and sum up 32 m over pi d cubed. For the tau, the equation that we derived earlier, radius equals to diameter over 2. J is right here. Just plug in pi over 2, radius to the power of 4. To sum up, 16t over pi d cubed. These two equations are so commonly used in this textbook because it shows up so many times. And so I recommend you guys, you can just memorize these two equations. So sigma equals to 32m over pi d cubed, tau equals to 16t over pi d cubed. It was very commonly used. Okay? Because we have shaft designs all the time. Now, this is the just proof of why Ix and J for a circular cross-section equals to what I showed you earlier, right? So I'm not going to prove them in the class. This is just for you to review. If you are someone who enjoys math, you can try it. Okay, like me, I enjoy math, so I figured, hey, let me prove it. But it requires some time to prove, so I'm not going to spend time here. But you guys can try it. It's quite fun. Okay? So this is just for your reference. Now, overall, left hand side normal stress, right hand side shearing stress. For the shaft, the normal stress equals to 32 m over pi d cube. For the right hand side, for the tau equals to 16 t over pi d cube. Okay. Now, let's take a look at a practical example where you have a shaft like this. You have both bending and twisting, right? Now, if you focus on different positions of the shaft, you'll realize that element lying on different positions carries different kinds of loads. Just like I mentioned earlier in the first slide, the material have stresses everywhere. So let's take a look at this particular one on the top. Because you are bending this way. You're bending this way. So the point on the top is being stretched, left and right, being stretched. So over here, left and right, being stretched. Okay? Now, how about twisting? Twisting is all the way, so over here on the right hand side of the material, there is a kind of twisting going this way. And on the left hand side of the material, there's a twisting torque going this way. So it's going like this, right? So if you eyeball on the square from the top, there are twisting going this way. But this kind of couple, if you have same force going different direction, same amount but different direction, with a distance between them, it's called a couple, right? A couple, force couple. So usually the force couple will be balanced by a different force couple. That's why if you have this, both doing clockwise moment, there must be some kind of force couple going the other way, so it balances out, making it going counterclockwise. That's why you have these two forces on the top and the bottom forming a balancing force couple. So doing like this to balance out these two force couples going this way. Okay? They exist at the same time. Otherwise, there's no balance of moment. Okay? So, for this particular material, if you have if you can have some kind of device that visualize the force, you will see a drawing like this. But there's nothing like this in the real life. But anyway, that's how the force is being applied on the top of this shaft. If you bend and twist simultaneously. How about the point on the side? Because it's on the side and lying on the neutral plane for bending, so actually no forces left to right. So over here there's no horizontal forces, but the twisting is still there. So same amount of twisting. And how large are those normal stresses and shearing stresses? Basically, you can just apply the equation that we derived earlier. Okay, the 32m over pi d cube and 16t over pi d cube. Okay, so from here you can already see we can analyze the stresses somewhere inside the shaft. So there would be, if we just compare these 2 points, this guy is carrying more stress. So if we are truly bending a shaft and then twisting the shaft at the same time, somewhere on the top edge of this shaft is carrying more loads. Actually, the most loads. So if someone somewhere has to break, probably on the top, or somewhere at the bottom. Okay. So if some part of the geometry is carrying the most load, and probably will fail first. Do we care about other points? Actually, we don't. Because this one fails first. If this point fails, the whole design fails. So we will never care about the other points that will not fail first. So in mechanical design, we need to find out where is the worst case position that point fails first. So if that point is safe, then we are safe. Okay? Oh, that's the end of this PowerPoint. Now I can move on because we have time. Let me see. So I'm going to move on to the next PowerPoint. I may not finish the whole thing. So this is what I'm supposed to cover tomorrow, but I will do something today. So tomorrow we will have less pressure. So now, actually I feel like this is a very troublesome problem, like a beam problem, okay? Because, so you guys remember this, right? You need to draw the shearing diagram and the bend moment diagram. Do you remember? I really don't like this part because sometimes it's easy to make mistakes. It's fun, but you can easily make a mistake. And I feel like for the entire book, this part is the most difficult part because the entire calculation takes a long process. But it's important, very important, because you need to know which point has that is carrying the most load. So for a shaft, because let me show you some example. Oh, not in here. Maybe in a future slide. Maybe this one. For a problem like this, right? So over here you can see it's this is a shaft, and the blue represent a bearing. One bearing here, the other bearing here. So this shaft is free to spin, and there are two pulleys being applied. Pulley is a 皮带轮, okay? Pulleys applied on the shaft. So they are having some forces applied to the shaft. The shaft is being twisted due to the pulley forces. So we need to know whether this shaft is safe enough. And after a bunch of calculation at the end, at the end you realize, oh, somewhere inside the shaft, like somewhere here, this is the weakest point based on the problem. So if this shaft could break, that is a position that could break. So if I want to make this shaft stronger, maybe I should do some dimensional change on that particular spot. Okay, so it's very important. Okay, and let's take a look at the course schedule. Today I go through one slide. Tomorrow I will talk about the beam problem, and I will give you a homework, just like this, just like something just like this. And we will have, do you know, we have exams. We have exams. exams? Here. Exam 1. So, next Tuesday is Moon Festival. Next Wednesday, we already have first exam. So what's the problem for the first exam? This problem, but different geometry. Okay, so I feel like you have learned all these, but in this course we have to go really fast, because I have to assume you already know that this week is just to remind you, hey, you have learned this. Now get those back. And you need to be able to solve the mechanics inside the shaft. And next week we have an exam. Then I need to talk about new stuff for the course, failure and fatigue. They require some time. Okay? Now maybe maybe I can cover a little bit. So tomorrow I can talk more. So let me continue on what I would like to say for the beam problem. So let me cover this. Okay, so for a beam, you can treat it as a simpler problem. It's a 2D problem. Okay, so everything is the same along the z direction, and you can have any kinds of forces distributed somewhere on the beam. But if you focus on one spot, a tiny spot, then this tiny cut looks like this. So above the beam, there are some distributed loads, and the magnitude of the distributed load equals to W. W could be different at different positions. But right here, because this width is super small, so this is super small, and the force amount on the top remains constant value W. Okay? So on the left, so this, because of the any arbitrary load carries on the apply on the beam, and it could generate both shearing forces and bending moment. So you have to say, on the left edge of this material, there could be certain amount of shearing force V. It could either go up or go down. It doesn't matter. So we just say, okay, let's draw this shearing force up on the left, and then let's say there's a bending moment on the left as well. So if there's a balance, then on the right hand side, we should have the same amount of V and moment. But because of the external forces on the top, it could be making some change to the shearing force and the moment. So we say on the right hand side, the pairing shearing forces could be having the same amount with a slight change. We don't know how much the change is, but there could be a slight change. The change could be zero, but there could be a change. Similarly, for the moment, there could be the same amount of moment m, or there could be a slight change due to the external force. So let's just, if this is a scenario, what would be the balance of forces and balance of moment? So we apply balance of forces, everything going toward a linear direction, basically up and down, can be written here. So this is a distributed load. So how do you compute the equivalent load? So the unit for W equals to force over length. So if you want to compute how much force is being applied on the top, you need to use this W times total length. So W times total length, which is dx. That equals to the total force on the top. Okay, so this is a total force on the top, plus there's a force going up, V right here, equals to all the forces going down, which is V plus dV. So these two V's balance out. At the end, we found out W equals to dV over dx. So if W equals to 0, then dV equals to 0. That means if there's no external force here, there's no increment of shearing force. But if there is W, either going up or down, the shearing forces is going to change from left to right. What's the amount of change? Depends on how much force you have. So the relationship between the W and the increment of the shearing forces can be derived right here. Okay? Secondly, we will use balance of moment. So everything that rotates will be expressed right here. You can treat a center as a supporting point, and you need to figure out what will be generating moment about the center point. So right now, V plus dV is gonna generate some kind of clockwise moment with a half dx radius right here. So half of the dx times the force right here, that's clockwise, plus this V similarly will generate a clockwise moment about this point, also clockwise. So V plus dx over 2. And we have this moment is clockwise, so n right here, equals to this one, n plus dn, this is going counterclockwise. So on the right hand side of the equation. How about W? Yes, it will generate moment, but it's symmetric left to right. So the left part of the distributing loads generate clockwise moment, the right part generate counterclockwise moment, they balance out. So you don't even need to put in the equation. So over here, you can cross out some of the terms that is the same on the left-hand side and the right-hand side of the equation. At the end, you end up with V equals to dm over dx. What does that mean? That means if there's shear, there will be change of moment. So if there's shear force, your moment will change. Okay, so if there's no shear, then your moment doesn't change. So this load will generate change of shear, and the existence of shear will generate change of moment. So everything is how they are related. Okay? I think I can continue. Over here, we can actually use what we have learned to study how much deflection we have. So because this tiny structure is being bended, if you exaggerate how much is bended, you can see if there's a neutral point here, if you hold this point on the left, and this point will be bended up. So bended up to here. So along this y direction, the amount of this of increment along this y direction is called the deflection. Okay, so if we can compute how much this material is being deflected, it's being deflected a tiny bit. But if you accumulate the whole thing, then you know how this beam is being deflected. Okay, so that's why we are curious about this increment along y direction. But how do we do that? So we need to follow some kind of a geometrical derivation. First, we need to understand what this figure is about. So this geometry is being bended in a certain way. So it's being curled about a center of curvature. So there will be a radius of the curvature. So rho is the radius of the curvature. And there will be an angle right here. So this angle, this is the angle of this piece of pie is d theta. Okay, and right here, because of the similar of geometry, this angle, this tangent angle right here, theta, is basically is this angle. Theta is this angle. Okay, and right at, if this is the beam, and right at very tiny bit of the geometry, this tiny bit of geometry only contributes a tiny bit of this tiny increment on this theta. For every geometry, only contribute a tiny bit. Okay, so that's why, because this is super exaggerated. So it's weird to see theta and d theta looking like in a similar scale, but actually this is super thin. You don't see it. Okay. Now, because you have these, and you will see at the bottom edge, the length of the bottom edge is being elongated. So originally, the horizontal length is dx. Now it has a horizontal increment. And how do you compute this distance? It can be computed by the radius right here times the angle. So you have this arc length. And what's the angle right here? It's the d theta. So c d theta gives you this arc length. So if you have this arc length, this is basically the increment in length. So increment in length over its original length, which is dx, basically is the definition of strain. This is why you have this equation right here. And strain equals to what? Stress over Young's modulus. And Young's stress equals to what? MC over I, from what we have learned earlier for the beam. So from here, at the very left and the very right of this whole equation, we end up with crossing out c from both sides. So d theta over dx equals to m over ei. That's why we have this. So if you want to study the increment of this d theta, it's related to how much moment is being applied, the material property, and the cross-section geometry, I. Okay, that's first equation. Now, let's go through the second one. If you look at the entire curvature, this is the radius of the curvature times the d theta equals to the arc length. And the arc length right here basically equals to dx. That's why you have this equation. So over here, d theta over dx equals to 1 over rho. Did you see this and this are the same thing? So you can kind of relate them together. So what we're going to do right now is to study a tiny triangle right here. What is theta? Theta by itself over here in this geometry equals to tangent. Tangent theta equals to dy over dx. But because theta is very small, so tangent theta equals to theta. So theta now equals to dy over dx. And if we take the derivative of theta with respect to x, then we come out with d theta over dx. So on the right hand side you have second derivative of y with respect to x. And also this equation is the same from the second and the first equation, so d is equals to 1 over rho and also equals to m over ei. So what we want at the end actually is, how do we compute y, deflection? So y equals to taking double integral of m over ei. So as long as you know the moment at any point, if you take double integral, you can get deflection. So to sum up, there are relationships of y and m, okay? And if you, because we have v equals to dm over dx, so if you take one more derivative, you have a shear. If you take one more derivative, you have W. So deflection, moment, shear, and the distributed load, all four are related based on these equations. And they are having this differential relationship. So later on, usually what we are going to do is, for a beam, we have certain conditions, we will figure out, this will be the shearing diagram. So shearing forces, right? We have shears everywhere. And then you need to figure out, what would be the moment. And then once you have the moment, you can take the double integral of moment. Then you can have over EI, right? You have deflection. If you have moment, you take the integral twice, then you can have the deflection. So you can figure out for the beam, it's gonna deflect in a certain way. You can figure out what will be the Y everywhere. You know how the beam deflects. Okay, so that would be the training for this part. So please go back, go find out your solid mechanics handout in the past, notebook, or go online and check my slides. Tomorrow, we will use those to do a practice. Okay, I can show you what I'm going to do later on. I will talk about Mohr circle. So, because later on in the next exercise, when we solve this problem, we need to figure out, like this is the shear along y direction, this is the moment along y direction, and because this shaft is being the forces are being applied to the shaft along two different directions. So there are shears along z and moments along z as well. So after you have the moment, I think in this particular exercise I didn't study the deflection, but you can. Then we will focus on which point is having the worst case, and we will focus on study the Mohr circle. Because later on, tomorrow after I talk about Mohr circle, you will realize Mohr circle is a way to help you to observe a singular point in different orientation. So if an element is some forces is being applied to a point, and if you are viewing this element along certain coordinate, and then you may not figure out, along which orientation is carrying the strongest load. So Mohr circle helps you to figure out, actually you need to rotate your coordinate system in certain way, or view this in this way. Actually, along this observation coordinate, you realize the material is carrying certain strong load along the rotated coordinate. So the material would fail along that particular coordinate. So the purpose of Mohr circle is to rotate observer's viewpoint to figure out, okay, along this position, along this coordinate, the material carries the strongest load. So we should, from now on, study this material along this coordinate, so-called the principal stress coordinate. Okay, so please go back and review solid mechanics and then Mohr circle, because we need to do some calculations later on. And Mohr circle part is very important because later on for the safe design model, we need to study the model based on principal stresses. So the process of the mechanical design now becomes like this. You need to have so you have a geometry. You have a geometry. You carry loads, right? Of course, geometry and also materials defined, right? Carry loads, and then you do some analysis to figure out the stress, and you find out which position is carrying the worst load, basically the largest load, and you know where is the weakest, and then you need to analyze the stress in a proper coordinate. So actually you need to do Mohr circle to figure out what's the principal stress. And later on, for design equation, usually for the design equations, they are derived based on principal stresses. That's why you need to be able to analyze your geometry, your mechanical parts along this procedure, and then you need to get principal stresses, and then you can apply your design equation. And of course, nowadays we use computer to help us do that. But as a student, you need to learn how to do it without computers, right? So this course, the main purpose of this course is to teach you how to do those at the end, based on the design equation, figure out how safe the design is. If it's not safe enough, change the dimension or change the material or carry fewer loads. Okay? That's it for today. Tomorrow we will continue.